Hey folks, I hope y'all had a good weekend. Let's go ahead and get started. Last time we looked at what it meant for a graph to be planar. We saw that a graph is planar if it's possible to draw the graph so that edges don't intersect except at a vertex. And we saw as an example that K4 is planar. We usually draw K4 this way, but we could take this edge and move it to the outside, and we get this alternate representation of K4, and now none of the edges cross. And so K4 is planar. Whenever a graph is planar, then it divides the plane into disjoint regions that we call faces. And so in this example, K4 divides the plane up into four faces. We always count the exterior as one of the faces. So this has one face on the outside, and then 2, 3, and then 4. So the whole plane gets divided up into four pieces, and counting the outside as one of the pieces. Here's a different example. This graph has 7 vertices, 12 edges, and 7 faces. So each of the 6 triangles here, and then the outside is the 7th face. I want to go through this example just for a moment. Vertices, there are 12 edges, and there are 7 faces. And it turns out that, and this doesn't seem important right now, but if I start with a negative sign, take vertices minus edges plus faces, in this case I get the number 2. But it turns out that I can't get away from this number 2. If I were to stick out another edge, then I'd also gain another vertex, and now I have 8 vertices and 13 edges, and I still have 7 faces. And so that's still 2. If I were then to put another edge that connects this and creates a new face, well, then I have still 8 vertices. I've gone up an edge, but I've also gone up a face. And that still equals 2. And so adding a vertex that doesn't create a new face, or adding an edge that doesn't create a new face, gives me an extra vertex and an extra edge. Adding an edge that does create a new face gives me an extra edge and an extra face. If I were to take this vertex here and split it, would that change the total? Well, I'd gain a vertex, but then this used to be one edge and now it's 2 edges, so I also gain an edge. And so I still get 2. In fact, this is true for every connected planar graph, that the vertices minus the edges plus the faces always equals 2. And this is a constant that we can apply to any planar graph. And we can prove this theorem by induction. So we're going to induct on the number of edges. So let me start with the base case. We're going to let G, let me shrink my pen down here. Let G be the graph that just has one vertex. That's the smallest graph that we can have here. Then there's one vertex, there is one face, and there are no edges. And so vertices minus edges plus faces does equal 2. All right. So now let's look at the induction step. All right. Assume that for all graphs with, let's say, n edges, all connected planar graphs, vertices minus edges plus faces is equal to 2. Let G be a graph with n plus 1 edges. Okay. So now we want to show that this formula also holds for this graph. So we're going to look at two cases. Case 1, G is a tree. So if G is a tree, then G has no cycles. And so we know something about the tree, that will have vertices will be n plus 2. There'll be one more vertices in the number of edges. Edges will be n plus 1. And faces is just going to be 1 because G has no cycles. If all I have is a tree, then there's no closed off regions. The entire plane will just be one face. And then vertices plus edges minus faces. Minus edges plus faces, I keep getting this backwards, minus edges plus faces is equal to n plus 2 minus n plus 1 plus 1, which is equal to 2. So that's a case of which is G is not a tree. Case 2, G is not a tree. Then at least one of our edges is part of a cycle. So let, I can't call it E because E is the number of edges, not a specific edge. So let capital E be an edge which is part of a cycle. So before I start writing some math, let me show you what's about to happen here. So I have here a cycle, and E is one of the edges in that cycle. Because this is a cycle, the inside of the cycle and the outside of the cycle are two different faces. If I delete this edge, then I lose one of the edges, but these two faces then merge together, and I also lose a face. Then G minus E has one fewer edge and one fewer face than G. But since G minus E has one fewer edges, then it has, G has n plus 1 edges. This means G minus E has n edges. And for all graphs with n edges, for all connected planar graphs with n edges, vertices minus n plus f equals 2. So vertices minus n plus f equals 2 for G minus E. and therefore vertices minus n plus 1 plus f plus 1. G has one extra edge and one extra face. So we have subtracted 1 and we've added 1. That didn't change the total. So this is also equal to 2 for G. And that finishes out the proof. If G is a tree, we didn't even need induction. We just used the fact that vertices is 1 more minus the edges, and there's a single face. If G is not a tree, then deleting an edge in a cycle deletes the edge and merges the two faces together. And so we get the formula for the smaller graph without the edge, and then when we put the edge back in, the edges go up, the faces go up, and they go up by the same amount, so we still have conservation of this 2. All right. So we have an exam on Saturday. And we are going to be using Wednesday and Friday as review days. So practice test is up. There is no more new material this week. So Wednesday and Friday will both be review days for this exam. All right. Y'all have fun. Take care. Thanks for coming.